Having in mind the Hellman-Feynman theorem, in order to have a useful approximation for the correlation energy functional, we are going to describe here the adiabatic connection. So the idea of the adiabatic connection is to have a continuous path between the non-interacting quantum system and the physical system, while keeping the ground state density constant. So we are going to keep in all this process the ground state density the same as the physical one. And that's going to be a key feature in all this process. An infinity of such paths are possible, but the most common one is consists on switching on the electron-electron interaction linearly with a coupling constant lambda. So that's going to be the lambda-dependent Hamiltonian we are going to consider in the system. Here we have the kinetic energy of the electrons. That's going to be now the new electron-electron potential energy. Basically is the usual one times lambda. And as if we just consider these two contributions, the ground density associated to that would be different. It wouldn't be constant. And we want it to be constant, which is going to be a key feature in order to apply these adiabatic connections. We have to add a new term, which is going to be lambda dependent. And this term is like an external potential operator imposing that the ground state density is the same as the ground state density of the physical system for all the lambda. So of course that external potential is going to be lambda dependent. This Hamiltonian reduced to the Kohn-Sham non-interacting Hamiltonian for lambda equals 0. Because in lambda equals 0, okay, we don't have this term, we don't have electron-electron interaction, that would be 0. But this would impose that the density for lambda equals 0 will be the same as the physical density. So that considering that the density will remain the same, the Kohn-Sham wave function we'll take from here will be the same for any lambda actually, because actually the density is the one that's going to impose, going to fix the ground state Kohn-Sham wave function. So actually the ground state, the Kohn-Sham wave functions are going to be independent of lambda. Besides that, for lambda equal 1, we are going back to the physical system. Okay. Once we have this Hamiltonian, lambda-dependent Hamiltonian, it's possible to define a universal functional associated to the system for each value of the parameter lambda. So, and we are defining this universal functional f in the usual way. That's the usual way to define the lambda-dependent universal functional. And lambda-dependent because in this case, the electron-electron potential that we are going to have is lambda times the usual electron-electron potential. And the wave function minimizing that, Hamiltonian is going to depend on the density, but also is going to depend on lambda, of course, because in the Hamiltonian we have a term which depends on lambda. And then besides that, considering the Kohn-Sham method, we can decompose that lambda-dependent functional in the usual way. So we have a non-interacting or the kinetic energy associated to the non-interacting electrons. Then we have that energy, the Hartree energy function is going to depend on lambda. The exchange energy function, that's going to depend on lambda as well. And then we have the correlation energy function is going to depend on lambda. And these three terms are going to depend on lambda. And what we are going to do next is going to see how they are going to depend on lambda. What's the dependence, the lambda dependence of these energy functions here? Because actually, our important aim here is to have an expression for this correlation energy here. So, first, we are going, in order to see the lambda dependence of these energy functions here, we're going to start with the Hartree energy functional. Okay, this is the Hartree energy function. This is the usual way of defining the Hartree energy function. As you can see here, the electron-electron potential we have now is lambda times the common electron-electron potential. So we have that the electron-electron potential here is lambda dependent. And it's linearly lambda dependent. And besides that, you have that the density is going to be the same as the density of the physical system. So therefore, we have that the lambda dependent Hartree energy function is going to be lambda times, because this lambda goes out, and you have here the Hartree energy function of the physical system. So this lambda dependent Hartree energy function is going to be lambda times the Hartree energy function of the physical system. So it's going to be linear in lambda as well. Okay, now let's go with the lambda dependent exchange energy function. So this is again the usual way of defining the exchange energy function. But in this case, of course, the electronic potential we have is lambda dependent. It's lambda times the common energy electron potential. So this is the average, therefore the average of the lambda times electron potential, considering on the constant wave functions. Again, as the density, we're keeping the density the same, the constant wave functions are going to be lambda independent, okay? And minus the lambda dependent Hartree energy function. So this is the exchange energy function. As you can see here, the only lambda dependence we have is here, and it can go out from this average. So this term is going to be linear lambda. This is also linear lambda. So therefore, we have that the lambda dependent exchange energy function is going to be lambda times the exchange energy function of the physical system. So we already did now the analyze the Hartree and the exchange energy functions, and now we are going to analyze the lambda dependence correlation energy function. So again, this is the usual way of defining the correlation energy function, which basically is all the rest which is not considering the non-interacting kinetic energy, Hartree, and exchange energies. So as you can see here, we have the average of the Hamiltonian, the kinetic, and the electron-electron potential, considering the physical, real minimizing wave functions, minus the Hamiltonians when we are considering the constant wave functions. And this expression here, that this energy function is going to be, it's non-linear in lambda. And this is very tough to do for many reasons, but one of the reasons is that depends on the kinetic energy, and this is tough to analyze. So how we are going to deal with that correlation energy function here? So for that, and that's where the Hellman-Feynman theorem enters. So what we are going to do here, we are going to do the lambda derivative of this correlation energy function. And when doing that, even though that wave function depends on lambda, as those are the minimizing wave functions of this Hamiltonian, the only remaining term when doing the lambda derivative is the lambda derivative of this Hamiltonian. And besides that, as the kinetic energy is lambda independent, the only remaining term when doing the lambda derivative is the electron potential energy, and that's important. So doing the lambda derivative of this term, it is really easy. And besides that, when doing the lambda derivative of this contribution here, it's also easy because the constant wave functions are independent of lambda. And again, the only remaining term is going to be the electron potential. So when doing the lambda derivative of the correlation energy functional and considering the Hellman-Feynman theorem, the resulting expression we have is this one. So sorry for that, this shouldn't be here. So this is the expression we have. Okay, and so the next step in order to get an expression for the correlation energy function is not, now we are going to do the integration over lambda. So we are going to integrate that over lambda from 0 to 1. Okay, when doing that, of course, we are going to have, because that's the lambda derivative, so doing the integration of this left term is going to be easy, because basically what we have is the correlation energy for lambda equal 1 minus the correlation energy for lambda equal 0. But the correlation energy for lambda equal 1 is the physical system. So basically, the correlation energy for lambda equal 1 is the correlation energy for the physical system, and we can write it this way. And the correlation energy for lambda equals 0. Lambda equals 0 is the constant system. So when you have a constant system, as you are considering the electrons to be independent, there is no correlation energy for the constant system. So the correlation energy for lambda equals 0, it's 0. So when doing the integration over lambda from 0 to 1, the only remaining term is going to be the correlation energy for the physical system. So of course, that's on the left, and we have to do, therefore, the integration on lambda on the right way, again, the same way. So this one is independent of lambda, so we don't need to do the integration of lambda of this term, because basically doing the integration of lambda from 0 to 1 is going to, we are going to take it 1, so it's going to be just, it's going to remain the same. So doing the integration of lambda of this term, considering what we have said before, that's the expression we have for the correlation energy. And the good thing about that is that we have an expression for the correlation energy functional that it's independent of the kinetic energy. And the bad thing about that is that in order to calculate the correlation energy here, we need the ground state of the physical system for all the lambdas going from 0 to 1. That expression is what's called the adiabatic connection formula here. And this is the one that is commonly used in order to have useful approximations for the correlation energies. And we are going to apply that expression here for precisely that aim. Have a closed expressions for the correlation energy and center the approximations that we need to make in order the correlation energy functionals to be useful.